So we'll start out mastering physics with this first problem here. So we have a plastic rod that's been charged to negative 15 nanocoulombs, touches a metal sphere, and afterwards the rod's charge is negative 10 nanocoulombs. We first want to know what kind of particles were transferred, and that has to be electrons, because electrons are the only thing that can move between two objects. The protons don't move. Next question, which direction was the charged particle transferred between the rod and the sphere? So the rod started out with a charge of negative 15 and ended with a charge of negative 10, which means it has less negative charge than it initially had. And so that means that the electrons transferred from the rod to the sphere. Okay, that's what was transferring, was electrons. They went from the rod to the sphere in order for the rod to become less negatively charged and the sphere to become more negatively charged. Last question asks how many particles were transferred. So for that, we're just going to go ahead and think about how much charge each electron has. So we know it was 5 nanocoulombs of charge transferred, which is 5 times 10 to the negative 9th coulombs, because that's what that nano means. Nano means 10 to the negative 9th. And so we're just going to convert that from coulombs to fundamental charge, the charge of an electron. So we know that one electron is 1.6 times 10 to the negative 19th coulombs, and this will allow us to find the number of electrons, and we end up getting an answer here of 3.125 times 10 to the 10th electrons. That's how many particles were transferred. So rounding to 2 sig or 3 sig figs here, we'll say 3.13 times 10 to the 10th. For this problem here, we have two masses that are 3 kilograms each and 1 meter apart, and they each have a charge of 10 microcoulombs. Okay, micro means 10 to the negative 6, so 1 times 10 to the negative 6 coulombs of charge. We want to know the force between them, so we're going to use Coulomb's law here. Fe equals K Q1 Q2 over R squared. So that electric force there is going to be 9 times 10 to the 9th. Times each charge, 1 times 10 to the negative 6, that's the charge on each of these particles here, all divided by the distance between them, which is 1 squared, and we end up getting an electric force here of 0.009, okay, newtons. If we put that to 2 sig figs, it's 0.0090, or 9.0 times 10 to the negative 3rd newtons. For the second part, we want to figure out the initial acceleration of each. And so for that, we're just going to be thinking about F equals ma. So the forces equals ma. The only force we have acting on them is Fe. So Fe is going to be equal to the mass of these objects, 3, times their acceleration. So 0.09 equals 3 times a, and that means that our acceleration here is going to be 0.003. Meters per second squared. Once again, if we want to put that to 2 sig figs, it would be 0.0030, or 3 times 10 to the negative 3rd meters per second squared. For this problem here, we have an arrangement of 3 charges, and we know that charge Q2 experiences no net electric force. We want to figure out what charge 1 is equal to here. So I'm going to start out by thinking about the direction of the force on these charges, and I'm going to assume that Q2 is just positive. It won't actually matter what Q2 is, because changing the sign of Q2 will just flip the direction of the forces. But let's assume it's positive, and I'm also going to call this charge here Q3. So let's think about the direction of our forces. So we first have a force between 2 and 3 going that way. 2 is going to be attracted to charge 3, and so that means that we must have a force going the opposite way between 1 and 2, so 1 must be a positive charge. If we did assume that Q2 was negative, what would happen is the force between 2 and 3 would go to the right. 1 would still have to be positive, though, because we'd want to draw the negatively charged Q2 to the left. So it really doesn't matter what you pick for Q2. It doesn't change what the charge is on Q1. Now that I've figured out what forces exist, I'm going to do an expression here for the magnitude of those forces. So the force between 2 and 3 is going to be K times charge 2, which is negative 2 nanocoulombs, or 2 times 10 to the negative 9th coulombs, right? That nano just means 10 to the negative ninth, okay, times Q2, all over the distance between them, which is 10 centimeters or 0.1 meters squared, okay. And then I'm going to do the force between 1 and 2. So F12 is going to be equal to K times, I don't know Q1 or Q2, divided by the distance between them, which is 20 centimeters or 0.2 meters squared. I know that these forces must be going in opposite directions to have no net electric force on charge 2. I also know that those forces must be equal. So I'm going to go ahead and set these two forces equal to each other. I could do a little bit of math and simplify some of this, but a lot of it's going to cancel out, so I'm not going to bother doing that. So we set those two forces equal to each other, and what we see here is that the K's cancel out, even though I could have subbed in for K. The Q2's cancel out, and from there I'm just going to cross multiply what is left, and so I'm going to get 0.4 times this 2 times 10 to the negative ninth, which gives me 8 times 10 to the negative 11th, is equal to 0.01 times Q1. So we go ahead and solve for Q1, and we get that Q1 is equal to 8 times 10 to the negative ninth coulombs. However, if we look closely, we actually want our answer here in nanocoulombs, not in coulombs. So what I'm going to go ahead and do is I'm going to convert that 8 times 10 to the negative ninth coulombs into nanocoulombs. So 1 times 10 to the negative ninth coulombs is 1 nanocoulomb. And that means that Q1 is equal to 8 nanocoulombs. Making it to 2 sig figs, I just say it's 8.0 nanocoulombs. For this problem here, I want to find the net force on the 1 nanocoulomb charge here that's at the top of the triangle. And we're just going to give the magnitude, and then for the second part, we're going to give the direction. So first of all, I'm going to go ahead and number these charges. I'll say this is charge 1, that's charge 2, and that is charge 3. And I'm going to think just about the direction of each force. So 1 and 2 are both positive. They are going to repel each other, so that means I'm going to have F12 going up like that. 1 and 3 are also both positive, so they also are going to repel each other, so I'm going to have F13 going up like that. What I'm going to do now is I'm going to go ahead and solve for the amount of force that I have here. All right. And so to do that, I'm going to do Coulomb's law, and what works out nicely is F12 and F13 happen to be equal to each other. These two charges are the same, and they're the same distance apart. So that makes my life a little bit easier here. I don't actually have to calculate those forces twice. So I'm just going to go ahead and solve for the amount of force I have, and that's going to be K times Q1, which is 1 times 10 to the negative ninth, times Q2, which is 2 times 10 to the negative ninth. Again, converting that nanocoulomb into coulombs. Nano just means 10 to the negative ninth. All divided by my distance, 1 centimeter, or 0.1 meters. And that's going to be squared. So when I go ahead and solve for that force, F12 or F13, both the same, I get an answer here of 0.00018 newtons, or 1.8 times 10 to the negative fourth newtons. Okay. Now that I have the amount for each force, I'm going to go ahead and combine those two forces, and to do that, I'm going to break them into their x and y components. What I end up seeing is two things. Number one, since they're both the same force at the same angle, these x components actually cancel out, so I only have to worry about my y components. The other thing is this angle in here ends up being 30 degrees. The reason I know that is that this angle here is 60 degrees, so that means that this angle here would also be 60 degrees. So both of those angles are 30. So what I can do is just solve for that y component of the force, which is just going to be F cosine of 30, so 0.001800018 times cosine of 30, and end up finding that the y component of that force ends up being 0.000156 newtons. Okay, so that's one y component. I'm just going to multiply that by 2 because I see there are two y components, both going in the same direction. And so I get that my net force here, acting on that top charge, is going to be 0.000 0.31 newtons. All right, and so there's my answer there for that first part. I know that that force is going to be 0.00031 newtons, or I also could have done 3.1 times 10 to the negative fourth newtons. And we want the angle here relative to the horizontal, so we know that force is directly up. Okay, our horizontal would be like this, so that angle there is just going to be 90 degrees. For this problem, we have a hairdryer that's drawing a current of 10 amps, and the first question we want to know is how much charge flows through the hairdryer in 2 minutes. So we know that current is equal to the amount of charge, delta Q, over the time. So we can just plug in these numbers that we know here. We know our current is 10 amps. Our time is 2 minutes, which we need to convert. So 1 minute is going to be 60 seconds, and so our time is actually going to be 120 seconds. So we'll put that in for our time, and that's going to allow us to solve for the amount of charge. And we end up finding that our charge here is going to be 1,200 coulombs. Okay, already rounded to 2 sig figs, so we can just put that as our answer. For the second part, we want to know how many electrons flow through it, so we can take that 1,200 coulombs and just convert that to electrons. We know that 1.6 times 10 to the negative 19th coulombs is the equivalent of 1 electron, and so we end up getting 7.5 times 10 to the 21st electrons make up that 12,000 or 1,200 coulombs. For this problem here, we have some currents flowing through some wires, and we're going to make use of our junction rule, the fact that whatever current goes into a junction must be the current that leaves it. So we know that IA here is going to be 6 amps, so that means there's 6 amps flowing through this, and we know that ID here is going to be 1 amp. Okay, so I'm going to first look at this junction here. We know that 7 amps goes into it, 6 amps goes straight, which means the remainder must go to the right here, and so that's going to be 1 amp for IC, all right, because 7 went in, 7 needs to come out, and then that 1 amp is going to combine here in this junction with the 1 amp from ID, and those two are going to combine to make a total of 2 amps going up there to IB, because whatever current, we know once again whatever current goes into the junction is the current that must leave the junction, so IB is going to be 2 amps. For this problem, we have an 85 watt blanket. That there is going to be the power, runs at 24 volts. That obviously is the voltage. And we want to find both the resistance of the wire in the blanket and how much current the wire carries. So I'm going to start by using this power equals voltage times current. All right, we know we have a power here of 85 watts. That's going to be equal to my voltage, which is 24, times my current. So I go ahead and solve this for my current, and I find that my current here is going to be 3.54 amps. I can then use that current in Ohm's law, V equals IR, to solve for my resistance. So my voltage is 24. I just found that my current is 3.54, and I can solve for my resistance, and so I get a resistance here of 6.78 ohms. And then I can go ahead and plug in those answers. We want both of them to 2 sig figs. So 6.78 ohms is really just going to be 6.8 ohms when rounded to 2 sig figs. And my current there of 3.54 is just going to round to 3.5 amps when we round it to 2 sig figs. Moving on to this problem here, we want to find the resistance between these 2 points, here and here. So you can almost imagine this being hooked up to a battery somewhere there like that. And that would complete our circuit. So we're going to look for simple combinations here. I'm going to start with those 2 resistors that are connected in parallel. So we can say 1 over RT equals 1 over 30 plus 1 over 45. We go ahead and solve for that. We find that our total resistance there ends up being 18 ohms when we combine those 2 in parallel. We'll now redraw our circuit, replacing those 2 with an 18 ohm resistor. All right, we've now redrawn our circuit, and we're going to look for our next simple combination, and that's going to be these 2 resistors here. They're connected in series, so the total resistance is just going to be 42 plus 18, which gives us 60 ohms. We'll now redraw it one last time, and we'll be able to solve. So now we've replaced that 42 and 18 with a single 60 ohm resistor. We see now our final combination is just these two connected in parallel. So 1 over RT equals 1 over 60 plus 1 over 40. And when we go ahead and solve for that, we end up getting a total resistance here of 24 ohms. And so we can just put that in there as our final answer. For this problem here, we know that three identical resistors have an equivalent resistance of 35 ohms. That's the same as saying the total resistance when they're all connected in parallel. And we want to know what is their equivalent resistance when they're all connected in series. So the first thing I'm going to do is I'm going to think about resistors connected in parallel and how they add up. 1 over R1 plus 1 over R2 plus 1 over R3 gives me 1 over my total resistance. So I know my total resistance is 35. I also know that each one is identical, so I can just say 1 over R plus 1 over R plus 1 over R. And so 1 over 35 is equal to 3 over R when I combine all of those. And I can cross multiply, and I find that R is just going to be equal to 3 times 35, or 105 ohms. So that's the resistance of a single resistor. Okay. I'm now going to think about what happens when they're connected in series. And so in series, we're just going to add up each individual resistance here. And so it's going to be 105 times 3, since they're all identical. And so I get a total resistance when connected in series of 315 ohms. All right, rounded to 2 sig figs, like the problem asked, that just ends up becoming 320 ohms. All right, for this problem, we have part of a circuit here, and we know some information about different parts of the circuit, and we want to determine the value of this resistor here, R. So I know that I have 2.5 amps of current running through this resistor here. It's going to get to this junction, and it's going to split, so I'm going to go ahead and just use my junction rule. I know that 1.5 amps goes that way, which means the remaining 1 amp must flow through this resistor here. So that's useful information. We can find some things with that. I also know the resistance and current of this particular resistor, so I can use Ohm's law, V equals IR, to solve for the voltage across it. So it's going to be 1.5 times 200, or 300 volts, are across this resistor. And since these two are connected in parallel, I know that the voltage across this resistor will also be 300 volts. So using that information about this resistor, I can go ahead and solve for its resistance using Ohm's law. V equals IR. I know there's 300 volts across it. My current is 1 amp, and so I can go ahead and solve for my resistance, and I find that my resistance is equal to 300 ohms. And that's going to be my answer there. It doesn't specify a number of sig figs, but the units would be ohms. Alright, for this problem here, we have a circuit, 10 volts connected to 4 5-ohm resistors in a combination of series and parallel. We ultimately want to find the voltage and current through each resistor. That's what all these questions are asking about. So I'm going to kind of move this aside for now, and we're just going to focus on this circuit and do a complete analysis of that circuit right there. So the first thing I'm going to do here is look for simple combinations, ultimately trying to find the total resistance of this circuit. So I see those 3 resistors all connected in parallel, and so I can go ahead and solve for the total resistance of those 3. And I find that the total resistance there is 1.67 ohms. Okay, and I can go ahead and redraw my circuit, replacing those 3 with a single 1.67 ohm resistor. Now I have my circuit redrawn, and I see that these two are now a simple combination. They're just connected in series, and so I can solve for the total resistance of those two by just adding them up, and so I end up getting a total resistance here of 6.67 ohms. So that's the total resistance of my circuit. I'm now going to use Ohm's law to go ahead and find the amount of current that left my battery, keeping in mind that my battery here has a voltage of 10 volts. And so using Ohm's law, V equals IR, I can find the total current that left the battery. So 10 equals I times my resistance, 6.67. And if you didn't round it all, because this is really 6.67 repeating, you end up getting a current here of 1.5 amps leaving the battery. So 1.5 amps is going to go ahead and leave this battery, and I can use that then to solve for the voltage across these two resistors. And so the voltage across this first resistor here is going to get 1.5 amps and 7.5 volts. That means my other resistor here is going to get 1.5 amps as well, because that current continues on through, and its voltage is going to be 2.5 volts. I'm now going to step this back one here, so this 5 ohm resistor was this one here, so nothing has changed there, so that means this resistor gets 1.5 amps and 7.5 volts. However, this 1.67 ohm resistor really came from these three all connected in parallel. Since they're connected in parallel, each one of them is going to get 2.5 volts across it, okay, because when they're connected in parallel, they all get the same voltage. That also matches with our loop rule. If this one gets 7.5 volts, that one needs to get 2.5 to add up to the 10, and same thing for the other two pathways. Using Ohm's law then, once again, V equals IR, I can solve for the current through each one of these resistors, and I end up getting 0.5 amps through each one of these resistors. Now that I've done that complete circuit analysis, it's just a matter of plugging in the right numbers back into my answers. So for resistor A, the first question, the current through is going to be 1.5 amps, and the voltage across it is 7.5 volts. That's just this resistor here. Moving on to resistor B, the current through that resistor is going to be 0.5 amps, and the voltage across it is 2.5 volts. Moving on to resistor C here, that one also gets 0.5 amps and 2.5 volts, and resistor D is also the same. They happen to all be the same in this case, but that's not necessarily the case. 0.5 amps and 2.5 volts. For this problem here, we once again want to analyze this circuit and ultimately find the voltage and current through all these resistors. So I'm just going to go ahead and do a complete circuit analysis, and then we'll worry about filling in the answers. So I'm going to start with my circuit here, and I'm going to look for simple combinations that I can eventually combine. So C and D here I see are just connected in series, so the total resistance is just going to be the sum of those two resistors, and so they end up having an equivalent resistance here of 10 ohms. Now I'm going to go ahead and redraw my circuit and replace those two resistors, C and D, with a single 10 ohm resistor. So we've replaced that one resistor with a single 10 ohm resistor. We can now look for the next simple combination, and that would be those two 10 ohms in parallel. So I'm going to add them up. 1 over the total resistance is 1 over 10 plus 1 over 10, which means the total resistance of those two is 5 ohms. I'll redraw my circuit one more time, replacing the two 10s with a single 5 ohm resistor. I've replaced those two 10s with a single 5 ohm, and now I have one last combination here, those two 5s connected in series, and so I can just add them up to get a total resistance here of 10 ohms for my circuit. I'm now going to go ahead and find the total current flowing through my circuit, keeping in mind, and it says this in the initial part, that this E here, this battery, is 15 volts. So using Ohm's law, V equals IR, I'm going to solve for my total current. So 15 equals I times 10. So the total current flowing through my circuit here is 1.5 amps. So 1.5 amps leaves my battery. That means that 1.5 amps is going to flow through that 5 ohm, and 1.5 amps is going to flow through that 5 ohm as well. I can then go ahead and solve for my voltage on each. So this is going to be 7.5 volts, and that's going to be 7.5 volts. I'll step this back one drawing here. So that 5 ohm was already there. That doesn't change at all, 1.5 amps and 7.5 volts. However, this 5 ohm resistor came from combining these two in parallel. So that means that each one of these resistors gets 7.5 volts across it. And we can use Ohm's law to solve for the current, V equals IR. So each one gets 0.75 amps of current running through it. I'll step this back one final time. And so I have this 5 ohm resistor here. That doesn't change at all. So 1.5 amps and 7.5 volts. This 10 ohm resistor is the same, 7.5 volts and 0.75 amps. And then these two resistors here, these two 5 ohms, combine to be this 10 ohm. Since they were connected in series, that means that each one get 0.75 amps of current flowing through it. And then the voltage, we can just do V equals IR to get, and so each one will have 3.75 volts across it. Now that we've solved for all these, we can start filling in the values we know. So for resistor A, which was this top resistor here, the current running through it is going to be 1.5 amps. The potential difference across it is going to be 7.5 volts. For resistor B, which is this one here, we see that the current running through it is going to be 0.75 amps, and the voltage across it is going to be 7.5 volts. Moving on to the next few here, resistor C, which is this one here, is going to have a current of 0.75 amps as well, and 3.75 volts. And resistor D is the same thing, 0.75 amps and 3.75 volts. If we want to do 2 sig figs, this technically should be 3.8 volts and 3.8 volts, but I think Mastering Physics will accept the 375.